As promised, we're back with grade 12 Euclidean Geometry, which a lot of people find quite challenging, and not exclusively because these questions are often towards the end of your exam paper if you're writing DBE exams. Okay, so what's important as your background knowledge, there's lots, but please do remember from grade 10, all the properties of quadrilaterals can still come back here. And your midpoint theorem. Your midpoint theorem is actually a special case of the proportionality theorem, but it's a very useful one to pull out of the bag when you get stuck. As far as grade 11 is concerned, 9 circle theorems, 3 groups of 3, remember, the circle centers, the cyclic quads, and the tangent theorems. And then there's also the 2 corollaries. Also remember your converse theorems for proving cyclic quads. So see if you can remember the 3 different ways of proving a cyclic quad. And can you remember 2 different ways of proving a tangent? In grade 12, it's just proportionality theorem with its converse and the similarity theorem with its converse. Then you've got the theorem of Pythagoras. And you've got the 3 right-angled triangles theorem. Okay, if you're not familiar with this one, go and have a look in your textbook. The textbook says if you have a right-angled triangle and you drop a perpendicular from the right angle to the opposite side, you will automatically have 3 right-angled triangles. It's actually very easy to prove. You don't have to know how. Very easy to prove. And so that's another one that you can pull out of the hat if you're really stuck. Or if you're just in a hurry and you need to save some time. Okay, let's have a look at a couple of questions. I'm going to do these questions in a couple at a time in the video because they can end up being quite long. Right, first up, they've given us a circle with center O. They've told us that O is the center of the circle. And so straight away, we know that we have radii. Those are the only 2 that are radii, by the way, so don't go make assumptions. We don't have a diameter because we don't have a line going through the center to the opposite side of the circle. They tell us that points A, B, and C lie on the circle. DCE is a tangent. Okay, so this guy is important. So the moment I see tangent, I'm thinking of 2 things. I'm thinking of tan chord theorem, which is super tempting because here sits an angle Y between the tangent and the chord BC. So angle between tangent and chord is equal to the angle subtended in the alternate segment. I also need to remember to look for radius perpendicular to tangent, and there it is, radius tangent. It's the tan rad theorem. So I have some 90s as well. Obviously, this side is also 90. Okay, then they tell me GOC is a straight line, BOJ is a straight line, and GJF is a straight line. Okay, F and H are points on AC such that we have parallel lines. It is never a waste to sit and read through the description and pick up some of the important points. Parallel lines, remember, alternate angles, corresponding angles, co-interior angles. They're still a thing. Right, we've got the Y, we've got the X, and then they also tell us FH to HC is 2:3. So 2x, 3x, 5x. Remember, we can't just write 2 and 3 because they didn't say 2 centimeters or 2 units. They said it's a ratio. So the x is there to tell us that the actual length might not be 2 and 3. back to this x for a moment. With my parallel lines, it's just far too tempting, so I'm going to put that angle equal to x because of the corresponding angles. Right, let's see what questions come up. It's always fun to see how much you've covered in the reading process. Okay, so first up, we've got to calculate, giving reasons, angle J1 in terms of x and y. Angle J1. All right, so angle J1, according to this, is an alternate angle to O3. All right, I don't know if I know anything special about O3 yet, but angle J1 is alternate to O3. O2 is x. They told me that BOJ was a straight line. So I have a feeling that O1 could be useful to me. So what you ask yourself is, where is angle O1? And the moment you say, oh, it's at the center of the circle, then you say, okay, O1 is therefore an angle at center. And you remember there's a theorem from grade 11 that says the angle at the center of a circle, subtended by a chord or arc, is twice the size of the angle subtended at the circumference by the same chord or arc. Okay, if you're battling to see this one, I'm going to just make it a bit clearer for you. As soon as I do that, I'm sure you can now see your angle at center. So if that angle is y, which we still have to substantiate, then O1 is 2y. And can you then see that O3 would be 180 minus x and minus 2y? And that would take me to J1. It's worth 6 marks. I have to justify what I've done quite carefully here. Okay, so what did I do? I'm going to be a bit like the TV chef here because we've actually written everything on the sketch. So the first thing I did was I said angle A is equal to y, and that was because of the tan chord theorem. Then I said O1 was 2y because of angle at center. And then I was able to say O3 is 180 minus these two, which is 180 minus x minus 2y. And lastly, J1 is the same size, y, because of alternate angles, GF parallel to OH. Remember, you have to put the parallel lines in if you quote alternate angles are equal. Right, so that was question 1 for 6 marks. It's definitely worth 6 marks. Let's have a look at question 1.2. Determine, giving reasons, the value of GO to GC. All right, so here come these parallel lines again. As soon as I see a ratio, there's 2 options, similarity or proportionality. If it's only 3 marks, then I would have to first prove 2 triangles similar. That's not going to happen in 3 marks. So I am very likely to go with proportionality. Right, can you see that I have got a triangle with one line parallel to the base of the triangle? Okay, so line parallel, one side of triangle. So therefore, GO over GC must be the same as FH over FC. And I already have FH over FC. So now I can state that they're equal. So TV chef again. Let's have a look over here. So GO over GC is the same as FH over FC. Why? Line parallel one side of triangle CFG, or you could have said proper theorem, OH parallel to GF. So now all I've got to do is fill in the measurements that I've used. So GO over GC is going to be 2P over 5P, which is 2:5, and that's worth 3 marks. Statement, reason, statement. Okay, so there's a lovely example where grade 11 and grade 12 Euclidean geometry are tied together to get us a quite nice matric question. Have a look at another one over here. Right, in this one, they tell us in the diagram below, A, B, C, and D lie on the circle with center O. All right, so if they're on the circle with center O, then we've got potentially a diameter here. We'll have to check if it's a straight line. And then A, B, C, and D are all points on the edge of the circle. So technically it's a cyclic quad. We would have to join AD to force it into a proper cyclic quad. Okay, but we could just as well use the bow tie, the butterfly, and talk about angles in same segment, which is probably what they're after over here. So AOFC is a straight line. Hooray. That means it is definitely a diameter. So that is definitely an angle in the semicircle. Then they tell me that DF is equal to FB. So this is your theorem 1. Your theorem 1 tells you that the line from the center of a circle bisecting the chord, so to the midpoint of the chord, is also perpendicular to the chord. Okay? And then they tell me that angle D is equal to X. Right, so I've got a 90-degree over there. I've got a right angle over there. This angle is equal to X. We spoke about the potential for the butterfly. So that means I have an X up there as well. Okay. Questions to be asked. Well, the very first question they ask is, in fact, what is the size of angle A? And so I'm going to just say in terms of X, angle A is X because of angles in same segment. From there, they're actually asking me for angle C3. So to get all 3 marks, I'm going to have to talk about the 90. So first going to say angle, let me write in pen so it's clearer. Angle ABC is 90. Angle in semicircle. Therefore, C3 is going to be 180 minus 90 minus X. So that's going to be 90 minus X, and that would be angle sum of triangle or something similar. Okay, right. So now I should fill in that 90 minus X, because maybe it's going to help me again. Right, I've got to prove, giving reasons, that F2 is equal to F3. Okay, so angle F2 is equal to F3. Well, that's going to be very straightforward now because we've got the line from center to midpoint of chord. So I'm just going to say F2 is equal to F3 is equal to 90 degrees, line from center to midpoint chord. That one's sorted. 2 marks in the bag. Right, now I've got to prove similar triangles. Triangle CFB, let's have a look for that. Triangle CFB. And I'm trying to prove that that is similar to triangle CBA. All right. If you're very wide awake, then you can actually straight away use the right-angled triangle theorem that I mentioned in the introduction. The 3 right-angled triangles. You've got a right angle here. You're dropping a perpendicular from the right angle. And so we automatically have 3 right-angled triangles. Okay, but let's just suppose for a minute that you didn't remember that. So we've stated that this is 90. We've stated that this is 90. We've said that that is x. So therefore, B1 has to be 90 minus x. So if I now compare the yellow triangle to the pink one, we've got C3 is 90 minus x and B1 is 90 minus x. We've got the whole of angle B is 90, and we've got F1 is 90. So we actually have enough information to prove the pink and yellow triangles similar to each other. Remember, when they ask you to prove that 2 triangles are similar, I'm going to use my TV chef solution here. So these are the 2 triangles that they gave me. So what you can do is you can straight away say, why is angle C equal to angle C? Okay, so if we go and look on the sketch, why is angle C yellow equal to angle C pink? Oh, it's a common angle. Okay. Then you can say, why is F equal to B? So let's have a look. F would be F1. Why is F1 equal to B? Oh, because they're both right angles. We've proved it. And therefore, angle B2 is equal to angle A because of the third angles of triangles. So triangle CFB is similar to CBA because of angle, angle, angle. All right, remember I said you could also say 3 similar right-angled triangles. Right, next up, they want us to prove that DC squared is equal to FC times AC. DC squared is equal to FC times AC. Okay, so a little bit of a tip over here is that if they give you DC squared, chances are you want to bring DC twice into your proportion. Okay, something to do with your proportions. Okay, so we can say that angle FCD, triangle FCD, and triangle BCA are also similar to each other. Okay, why did I choose FCD? Because I needed to bring DC into the story. Okay, so let's get another color over here. Okay, So these two triangles are definitely congruent, okay? We've got the right angle, we've got the DF equal to FB, and we've got the common side. So side angle side means that the triangles are congruent. So now I'm saying that triangle, let's get my order right, FCD is similar to triangle BCA. Okay, there's the X, there's the X, there's the 90, there's the 90. I can also say that CD is equal to BC. Okay, so it really works out beautifully and quite simply. Triangle FCD is similar to triangle BCA. When I say above reason, it's also angle, 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 and because of congruent triangles. CD is equal to CB. Okay, sides opposite equal angles, if you like, or you can rather say congruent triangles. They don't expect you to spell out the congruency anymore. Okay, so from my similar triangles, I'm going to use my proportionality. So I'm going to say CD, because that's the one I'm really after, over CA is equal to FC over BC. Why did I choose that? Because BC can become CD, which is what I really want. Okay, so CD over CA, FC over BC, because of similar triangles. Therefore, CD times BC, cross multiplication, is equal to FC times AC. But because BC is equal to CD, which we've already proved, we can say CD squared is equal to FC times AC. Okay, so a little bit more higher level, but not really too terrible. If it really worries you, you can write here BC equals CD. Okay, now for the scary one. The scary one looks like that. FC over AC is supposed to be equal to this huge, terrifying looking expression on the right. Okay, so the more I looked at that, the more I realized that I couldn't work with that. And then I noticed that actually it's just a difference of perfect squares. So I simplified it. And I said, let's multiply these two brackets together as a difference of squares. So it's a required to prove that FC over AC is rather equal to 1 times 1 is 1 minus AB squared at the bottom AO plus OC squared. Okay, it was still a little bit scary, but I went back to my sketch to see what is AO plus OC. So let's have a look. What is AO plus OC? Oh, it's just AC. So suddenly I'm expected to prove that FC over AC is 1 minus AB squared over AC squared. And then I started to think about good old Pythagoras. And I said, okay, I can see the AC squared, I can see the AB squared. So now I've got to bring in BC squared. But we've just worked with BC equal to DC. And so I started to feel quite clever. Okay, I'm going to show you a little bit further. So my required to prove right-hand side algebra brought me to 1 minus AB squared over AC squared. Okay, we've agreed on that. Which gives me common denominator AC squared at the top, AC squared minus AB squared. Ha! AC squared minus AB squared. So that must be BC squared. So my right-hand side is now BC squared over AC squared because of Pythag. But in my previous question, I proved that BC squared was equal to DC squared. And so my right-hand side has now become DC squared over AC squared. And then the real magic comes in. In my previous question, I proved that DC squared is equal to FC times AC. So DC squared over AC squared could be written as FC times AC over AC squared, and therefore it becomes FC over AC. So what have I proved? I've proved that the right-hand side, the messy one, can be reduced all the way to FC over AC. Horrible. Let me go back to the question. There it is. Prove that FC over AC is equal to the right-hand side. So I took it backwards. I started with the right and I ended with the left. So I proved left-hand side equals right-hand side. Okay, I'm going to put the solution back up on the screen for you so that you can actually see the process one more time. That was quite a challenging question, I would say. But there will be more Euclidean geometry videos. This is just the first one, just to whet your appetite and hopefully for you to see that the questions, some of them will be very easy marks and some of them will be quite challenging.